Hello, welcome to this video where we'll learn about the soil states and their volume calculations. You will learn about the volume changes of the soil during its different states between the construction processes. You will also learn about the basic volumetric relationships between the soil states so you can calculate the soil volumes for the different construction operations. Let's follow the life story of a cubic yard of a soil during a typical earth moving operation. In this earthwork or earth moving operation, the soil is excavated from a cut area in the site, transported to a fill area where it is compacted. So before the soil is excavated, we can measure its volume in its natural condition using topographical plans and survey. In its natural condition, the soil is called the bank to be in the bank state, and it is its volumetric measuring unit is differentiated by giving it a first name, bank. So like bank cubic meter PCM or bank cubic yard PCY. As you can see here, the soil is about to be excavated by a front hoe equipment. As the material is being excavated and loaded into the truck, the soil swells and loosens. It's called to be swelling, and its volume increases. So the 1 cubic yard of soil in its natural bank state will swell and increase to about 1.25 cubic yards for the shown example. Every soil type swells differently, like we'll see in the coming slides. After the soil swells during that excavation step, the soil changes from the bank state to the loose state. As such, we need to use the loose cubic yard LCY or loose cubic meter LCM as the units to measure the soil in this state to differentiate it from the volume calculations in the bank state. When the material is delivered to the fill area of the site, it's dumped and compacted to reduce volume to increase its density and strength. So the 1.25 loose cubic yard that we tracked so far will shrink to be 0.9 cubic yards. The mechanical energy applied by the compactor will compress the soil and tighten its inside voids. After the soil shrinks during that compaction step, the soil changes from the loose state to the compacted state. As such, we need to use the compacted cubic yard CCY or compacted cubic meters CCM as the units to measure the soil in this state to differentiate it from the volume calculations in the bank or loose states. In most of the cases, the compaction mechanical energy results in a compacted volume that's less than the soil's bank volume in its natural condition. The volume increase of the soil from its bank to loose state can be quantified using the swell percentage factor. So it's a value here, a percentile value, which can be calculated using the shown formula here. Swell percentage measures the percentage increase of the soil volume when it is excavated. During the swelling phenomena, the air voids of the soil expands for the same weight of solids and water. This means it's always expected that the loose density is less than the bank density, as you can see in this example. Using the shown values, the swell percentage is calculated to be 40%. This means that a 1 cubic meters of this soil material will expand to 1.4 loose cubic meters after excavation. Another way to measure the soil swelling is to use the load factor, which is the ratio between the loose and bank densities. You can also calculate it using the swell percentage. For the shown example, the load factor is calculated to be 0.714, which is the inverse of 1.4, or the swell 1 plus the swell percentage that we calculated before. A load factor of 0.714 means that 1 loose cubic meter of hold soil will need to excavate only 0.714 bank cubic meters of the soil in its natural state. Similar relations and parameters can be used to measure the volume reduction of the soil under compaction. When the soil is compacted, its volume is reduced by squeezing its air voids while the water and solids stay the same. This means that the volume is decreased for the same weight or mass, which translates in more density for the soil and compacted compared to its bank or loose density. You can see such density difference by the shown example here for the bank and compacted density. So the compacted density is more than the bank density. The parameter we'll use in this volumetric relationship is called shrinkage percentage. It's calculated as the shown value using the bank and compacted densities. The shrinkage percentage is used to measure the percentage that the soil volume will decrease when compacted. For the shown example density values, the shrinkage percentage is calculated to be 20%. This means that the compaction of 1 bank cubic meter of the soil will make it shrink to 0.8 compacted cubic meter. The shrinkage factor is another way to describe the same soil behavior under compaction. The shrinkage factor is calculated as the ratio between the bank density and the compacted density. It can also be calculated using the shrinkage percentage value that if it is available for you. For the shown example density values, the shrinkage factor is calculated to be 0.8. This provides the same understanding we get from the shrinkage percentage, that a 1 bank cubic meter of the soil will shrink to 0.8 compacted cubic meter of the same soil. You can see the shrinkage parameters relate the bank to compacted states and skip the loose state. To relate the loose to the compacted states, you will need to use both the load and shrinkage factors. So here is a summary of the 4 main parameters that relate between the soil volumes and its bank, loose, and compacted states. Also, this table shows rough density and volume change parameters values for some soil types. The loose, bank, and compacted densities are given in both the pound per cubic meter and the pound per cubic meter, and kilogram per cubic pound per cubic yards and kilograms per cubic meters. The table shows only 4 soil types: clay, common earth, rock, and sand and gravel. You can see the big differences between the loose densities of different soils, ranging between 2310 up to 30,060 pound per cubic yard. But in the compacted state, the density deviation between the different soils decrease as the air voids are reduced. The highest swell occurs for the rocks. You can see here by the swell percentage. And this happens because the volume significantly increased from its natural state bank state as big boulders to change to loose blasted state. The least swell happens to the soil, to the sand and gravel, due to the small differences between the loose and bank density. The load factors here match the same values, are the same understanding that we can get from the swell percentage. And also, all of the load factor are less than 1. The rock exhibits the largest shrinkage percentage, but with a negative sign. How is that? You can understand the reason behind this weird value by examining the difference between the bank and compacted densities of the rock. Bank and compacted. Typically, the compacted density is more than the bank density, you can see from the other soils. Take a moment and examine these values. This is due to the fact that the mechanical energy applied during compaction results in less air voids than those that exist in the natural bank state. However, the blasted rock is a very special case. Rock exists as a solid chunk of boulder with a very little or zero voids inside it in the natural bank state. But blasting it results in breaking it down to smaller rocks with voids in between. This results in the bank density of the rock to be higher than its compacted density after blasting. Basically, it's not feasible anymore to compact the blasted rock back to be a big boulder. The negative shrinkage here means that the blasted rock doesn't really shrink under compaction relative to its natural state. So why we learn about the soil swelling and the shrinkage and their calculated parameters? The answer is planning and estimating of earthwork operations. Over the typical earthwork steps of excavation, hauling, and compaction, the soil exists in different states and measured with different units, as you can see here. The same soil is measured using BCM when it is excavated, and using LCM when it is hauled, and using CCM when it is compacted. So it is critical to match the correct unit of measuring the soil to the corresponding construction operation. Also, it's important to relate the volumes of the same soil between the different operations. As such, the shown formulas here will become handy when estimating the work scope, durations, and costs of the earthwork operations. The first two formulas relate the volumes in loose and bank states, while the other two formulas relate the compacted and bank states. You can use the first formula to calculate the loose volume of the soil based on its bank volume and load factor. The second formula is another way of relating the loose volume and bank volume by using the swell percentage. From the previous slide, you can easily relate the first and the second formula by relating the load factor and the swelling percentage. The third formula can be used to calculate the compacted volume of the soil using its bank volume and shrinkage percentage. The fourth formula is another way to relate the compacted and bank volumes by using the shrinkage percentage. You can clearly see that we substitute the shrinkage factor in the third formula with 1 minus shrinkage percentage in the fourth formula, which is one relation we learned from the previous slides. You can use the loose bank relation and the compacted bank relation to derive the relation between compacted and loose volumes. My hint to you, use the bank volume as the common term to link between the two provided volume relationships to derive the compacted loose volume relation. This is the end of this video, where you learned about the soil volume changes between the banked, loose, and compacted states. Also, you learned about the shrinkage and swell factors that will become very handy when you calculate the work scopes, productivity, and cost estimates for earthwork operations. Thanks for watching, and have a good day.